Okay, with this lecture I'm going to discuss the test that you wrote, the first semester test. What we will do in terms of the record for students watching the YouTube is we will take some screenshots of the test and the memo, and then we will add it to the end of the lecture. So if you don't know what this test is all about, it is all at the end and you can get all the details there. Okay. But in general, I think there were two questions. The first question is a theory question. The two flat plates, the derivation of it. It is very, very simple. I'm not going to spend time on that. I would like to spend time on question 2 to 5. The question may be a little bit different than what I've asked in previous years, but still actually a very good question. The essence of it is the cooling of wine, okay, originally at 20 degrees Celsius, would like it to get to 3 degrees Celsius. It is in ice. The ice is at a temperature of 0 and the heat transfer coefficient is 500 watts per square meter degree Celsius. And the essence is to determine how long will it take for the wine to cool from 23 degrees Celsius to 3 degrees. Okay, so that is the question, and we're going to use different methods to solve it and to critically discuss the different methods with each other to see what the limitations are and if we can trust them. Okay. The wine, we do not have the properties of wine, so we are making an assumption. We say that we need the properties, and if you go and look in the tables, you will see that the properties of K, rho, and Cp are functions of temperature. Now, the wine is going to be cooled from 23 degrees Celsius to 3, so it is a temperature difference, and the average temperature in between, if we take the average, would be about 13 degrees Celsius, and that is why I've selected the properties at 13 degrees Celsius. If you want to go and do the problem with the properties at 23 degrees Celsius and also with 0 degrees Celsius, and you'll see that in this case it would not really matter that much. And the reason for that is that the properties of water between 23 and 3, all these properties K, rho, and Cp, are not really strong functions of temperature. They are being influenced by temperature, but it's not significant. So it's not really a lot. Okay. So the first approach is to look at this problem and say that let's consider it in question 2 as a lumped system. With a lumped system approach, we need to get the characteristic length. And the characteristic length is determined by the volume, and in general, or let me do it like that. Let's first just sort of, let's get the length of the bottle. So we can say the volume is equal to pi divided by 4 multiplied by d squared multiplied by L. The volume is 750 milliliters. So in terms of cubic meters, 750 multiplied by 10 to the minus 6 equal to pi divided by 4. The diameter of the bottle is 0.0691 squared multiplied by L. So L is 0.2 meters, or then 200 millimeters. So just from the answer, you must ask yourself, does it make sense? So if you think of a wine bottle, typically 750 milliliters, if you would calculate, if you would assume it's a cylinder, and calculate the length, typically 200 millimeters makes sense. Okay. Oh my goodness. Can you stop the video, please? Is it fine now? Okay, you can roll now again? Is it on? Yeah. Okay. Okay, ladies and gentlemen, we've sorted out the technical problem. Let's go on. So we've calculated the length of the bottle, which is 200 millimeters, and now specifically for the lump system approach, the characteristic length is equal to the volume divided by the surface area. Okay? The volume we have is 740. We need the surface area. And the surface area we can calculate as, that is now our body like that. Okay? So we firstly have this area here, plus that area there at the top, plus 2 of them. Okay? So in the calculation of that is very easy. Let me just get it. So that would be equal to pi multiplied by the diameter multiplied by L plus 2 times pi divided by 4 d square multiplied, 2 times pi 4 divided by d square. Okay, so that is the surface area, and if you go and do the calculation, then it works out as 0.05092 square meters. Right, so now that we've got the surface area and the volume, we can calculate the characteristic length, and the characteristic length is then 750 milliliters. 750 multiplied by 10 to the minus 6 divided by the surface area. Here's the surface area, 0.05092, and that gives a characteristic length of 0.01473 meters. Okay. This approach is unique to the lump system approach. It's not a general approach in terms of the calculation of a characteristic length. So the Biot number, which is then equal to the heat transfer coefficient multiplied by the characteristic length divided by K, is equal to the heat transfer coefficient is 500. The characteristic length is 0.01473 meters divided by the thermal conductivity. Thermal conductivity is equal to 0.5732, and from this we can calculate the Biot number as 12.85. Okay. Now we know that when we've discussed this, we've said that the lump system approach is valid if the Biot number is typically smaller than 0.1. Where does that come from? It is a rule of thumb, and it means that it has to do with a ratio of the internal resistance to the outside. So the rule of thumb says that if this resistance is typically 10 times smaller than that, then the lump system approach will give us a good answer. This now means that this resistance here is 12 times more than that. So the lump system approach already, we know, is not really valid. Okay. But let's just do the calculation. And we do that by starting to say that we also need to calculate B. Okay. In the equation, the B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and Cp. Everything has been given and or determined, and that means that if we calculate B, it is equal to 0.008116. And we can also calculate the non-dimensionalized temperature. The non-dimensionalized temperature is the temperature in the body minus T infinite, Ti minus T infinite. The temperature that we want, the inside is 3, the temperature on the outside is 0. 23 is the initial temperature and the environment temperature 23, and that gives us a non-dimensionalized temperature of 0.1304. Where am I going with this? I'm going to the fact that very cryptically we can actually say for a lump system approach the non-dimensionalized temperature is equal to E to the minus BT. Okay? The non-dimensionalized temperature is that temperature there. It's E to the minus B, that term there. I've just written it a little bit more cryptic to make it easier. And everything is now known. The non-dimensionalized temperature is equal to 0.1304. It's equal to E to the minus B, 0.008116 multiplied by T. And from it we can calculate T as 251 seconds, which is 4.18 minutes. Right, so for those of you drinking wine, you will know that most probably that is not going to happen. The result already doesn't look right. Okay, do you agree? 4 minutes. If you take a bottle of wine at 20 degrees Celsius and put it in ice, getting to 3 degrees in about 4 minutes is most probably not going to happen. Why? Because the assumption of the Biot number is the problem. Okay. So in terms of the discussion, that was very important, is that firstly, you have to indicate that the lump system approach is valid only for Biot numbers, typically 0.1. Okay, that's the first reason. The second thing is that many students would actually come to me and say, but you know, if we look at this problem, then you must actually remember if this is the wine bottle, okay? Now, although we've said that we assume it is now a cylinder like that, it must have a certain thickness, and that thickness is of the glass, okay? Which is true, so we have to take that into consideration with our calculations. But if you go and look at the K of glass, thermal conductivity of glass, it is approximately 0.7 watts per meter Kelvin. If we look at the thermal conductivity of water, you would see they are about the same. So the glass or a thicker bottle of wine is not going to have an influence on this problem. Okay. The other thing that is important, however, is that, and we've discussed it previously, if you would now decide, I'm going to take the bottle of wine, and while it's in the ice, I'm going to shake it all the time, then that is going to change things, isn't it? Because now the thermal resistance on the inside is becoming much lower. So most probably, if you shake it very well, it can be done. Okay, so the shaking, we change the internal resistance on the inside and to maybe a Biot number of smaller than 0.1, and then maybe that is possible. It can be done maybe then. Okay. Right, so that's a lump system approach in terms of the calculation of the time that it will take before the temperature decreases from 23 degrees Celsius to 0 degrees Celsius. Any questions, ladies and gentlemen, on this problem? Okay, nothing? You're all happy with it? Right, let's go to the next one, and the next one, question 3, is about making the assumption that now it is a long cylinder. Okay. Okay. And let's draw it like this. So now it is a long cylinder, like that. And the cylinder diameter, still we keep it 96.1. Okay. And the conditions are exactly the same. Okay. We want to know how long is it going to be before the temperature is 0 degrees Celsius on the center. And take note, it is everywhere on that line, okay, on the center. On the outside, the ice or the water is at 0, the heat transfer coefficient is 500, and now determine how long is it going to take. So what is not being taken into consideration is the heat transfer from there and there. So if you look at this wine bottle, so we would consider all the heat transfer from there, and we would actually neglect the heat transfer in that direction. Okay? So we only look at the heat transfer in one direction and not in two directions. So for a cylinder, let's look at table 4.1 in terms of the calculations. That is the complicated equation, if you look at it like that. Okay, Aaron, if you can zoom on that equation for us for a moment. And the equation consists out of theta is equal to a constant, which is everything before the e to the minus lambda 1 squared tau term multiplied by J0 of lambda multiplied by r divided by r0. That is the equation fundamentally. Now in your textbook, the derivations has been given for the special case where we want it on the center. Okay. That would be when r is equal to 0. Okay. And the result of that is J0 in 0. Okay. Now where do we get that from? So if we look at the 0th order and 1st order Bessel functions, we can see that if it is equal to 0, then it is equal to 1. Okay? So this equation reduces to, at the center, that the temperature is equal to a constant multiplied by e to the minus lambda 1 squared multiplied by tau. The calculation of the Biot number, right, now we can say the Biot number is equal to 12.85. Is that correct? No, we cannot say that. This Biot number that we've calculated here has been calculated in a special way to ensure it works for the lump system approach. In the derivation of this equation, there was a number of values which came together and which made it easy in the derivation of the equation to call that a constant, and that constant is the Biot number. And that was defined as the heat transfer coefficient multiplied by R0 divided by K. Okay. The heat transfer coefficient is 500. The diameter is equal to 0.0691 divided by 2, divided by the thermal conductivity, which is equal to 0.5732. And the result is a Biot number of 30.14. Right. Now that doesn't mean if you look at this result that you must now look at it in terms of the previous work if it's smaller than 0.1 or larger than 0.1. That is not relevant at all. Remember, that criteria is only valid for the lump system. That is the Biot number, and if we now want for the Biot number the lambda and the A, we can get it from table 4.2. So at a Biot number of 30.14, there we look at it. Be very, very careful that you do not take the values for the plane wall or the sphere. So there we can see they are about 2.3261 and 1.59732. Many students would ask me, well, do I need to interpolate because it's not 30? Okay. Now, I do not have a very simple answer for you. Okay. You always have to use your judgment. Okay. Now, if I would look at those values of the Biot number between 30 and 40 of lambda and A1, it varies very, very little. You see, it is 2.34 and 2.345, and the other one 1.597 and 1.599. So they are very close. So it doesn't really make sense to try to interpolate. If the values were very, very low, very, very far apart from each other, then I think, unfortunately, you'll have to think of doing an interpolation. Okay, so with that Biot number, we can go and get the lambda, which is equal to 2.3261, and we can get A1, which is equal to 1.5973. Okay. So, in us making this assumption now of saying that the non-dimensionalized temperature is equal to A1 e to the minus lambda 1 square multiplied by tau, we make an assumption by saying that, well, we hope that tau is going to be larger than 0.2. Okay, because if it's not, then we do have a lot more work to be done. Okay, so we make that assumption. If we look at that, we've got A1 now, we've got lambda, we need to get tau, we need to calculate the non-dimensionalized temperature, which is very easy. So the non-dimensionalized temperature at the center would be equal to T0 minus T infinite divided by Ti minus T infinite, and that would be equal to 3 minus 0, again 23 minus 0, and that is equal to 0.1304. We've calculated it previously, but again, there is the non-dimensionalized temperature. So coming back to this equation, the non-dimensionalized temperature is equal to A1 e to the minus lambda 1 square multiplied by tau. We now have the non-dimensionalized temperature, 0.1304 is equal to A1, which is equal to 1.5973 e to the minus 2.3261 square multiplied by tau. Okay. And from that we can calculate tau as 0.463. So fortunately, our assumption is okay. We can use the non-dimensionalized, this approach of just using one term. Right, tau, the non-dimensionalized time, is equal to alpha t divided by R0 square. Okay, alpha is equal to K divided by rho Cp. Okay, K has been given as 0.5732, the density 999.4, and Cp 4185. So we can calculate alpha, which is then equal to 1.37 multiplied by 10 to the minus 7. And therefore, the non-dimensionalized time is equal to 0.473. It's equal to 1.37 multiplied by 10 to the minus 7 multiplied by t divided by r, 0.069 divided by 2 square. And from that, we can calculate the time as a little bit more than 4,000 seconds, 4,033 seconds, which is 67.21 minutes. Okay, 67.21 minutes. If we look at it critically now, very critically in terms of can we expect a good answer, then firstly, I would say yes, we can already expect a good answer. Okay. Obviously, we do have the assumption of the wine bottle making it a cylinder. The limitations would be that we neglect the heat transfer in the second dimension. Okay. We are only now with a wine bottle looking at the heat transfer in that direction. We know that there will also be heat transfer in that direction and in that direction. Okay. So we need to take that into consideration. Right. You all happy with that? No questions? Right. The next one is to say, well, let's consider it as a semi-infinite body, okay, semi-infinite solid, and we have to solve it now. Now there are 4 cases in the textbook that we've looked at in terms of boundary conditions. I think for this one it's very clear. The heat transfer coefficient is given. Okay, it's not a laser or the temperature on the wall is given. So case 3 gives the non-dimensionalized temperature. And the non-dimensionalized temperature is a long equation. Okay. I'm going to make it very simple now. I'm going to make it simple by saying it is equal to the error function multiplied by T1, a term, minus E to a value T2 multiplied by a complementary error function in T3. That is how the equation looks like. Now, the best advice I can give you, and there are going to be many examples in this course, that I want to ask you that please do not just start doing number crunching. Okay? I want you to take a look at the relative size of the terms, because that is very, very important. Okay. So if we look at the different terms, then we have the term T1, which is equal to x divided by 2 times lambda t. Okay. And if this is now our wine bottle, like that, then x would obviously be measured from the surface there. Okay. So that's the first term. The second term is equal to the heat transfer coefficient multiplied by x divided by k plus the heat transfer coefficient square multiplied by alpha t divided by k square. And then the third term is equal to x times 2 times this square root of alpha t plus the heat transfer coefficient multiplied by the square root of alpha t divided by k. Okay, so 3 terms there, a lot of work in terms of the calculation of getting the answer. And I wasn't very kind with you because I'm actually asking t, so which means that you have to end up in an process of iteration. Okay, so what would be nice, of course, is, with a complicated equation like this, is that if one of these terms are 0, okay, because then it makes things much, much easier. And that is indeed the case. So if we look at this term, T3, okay, and you can now decide that from this, I think a realistic time would be 5 minutes. Put in 5 minutes here and do all the calculation and see what is the relative size of the term. So that's the approach that I've used. I've said, well, let me use 5 minutes, okay? 5 minutes. And then I go and do the substitution, okay? And the result is that if I do that, that T3 would be equal to 8.3, okay? And if we now look at the tables, Aaron, if you can zoom in there for me. Okay. If we look at the tables, okay, if eta is 3.6, then we can see the complementary error function is along about 0, you see. And here you can already see, that if the error function starts becoming larger than about 2, then for all practical purposes 0. Okay. So with that value, if we look at that and we look at the complementary error function of 8.3, it's 0. Okay. And we've got 0 there multiplied by that, then everything on that side disappears, and the equation now reduces to a very, very simple equation that the non-dimensionalized temperature is equal to the complementary error function of T1, and T1 is just that term there. You see? Okay. How would you know that you can do that? Well, by doing a few problems in the textbook, and there were quite a few in the textbook that guided you through this and helped you to make this type of decision. Okay. You all happy with that? Okay. So The non-dimensionalized temperature, I'm not going to calculate it again, but, oh no, yeah, sorry, I have to do it. Yeah, because in this case, sorry, the non-dimensionalized temperature is now calculated differently. It is calculated as TXT minus TI divided by T infinite minus TI is equal to, we would like to know how long it will take before the temperature is 3 degrees there, minus TI, which is 23, 0 minus 23, and that gives a non-dimensionalized temperature of 0.8696. Okay, so, and that means 0.8696 is equal to the complementary error function of eta. Okay. So if we now look at this and look for when will the complementary error function be equal to 0.696? That will be when eta is equal to, you see there it is about. I want me to enlarge it for you. Okay, about there, you see? All agree? So from that we can now get eta as 0.1161. Okay. What is eta? Well, eta is equal to x divided by 2 times alpha t. Alpha, the non-dimensionalized, that value eta, sorry, is 0.1161 is equal to x, and x is at the center, which is equal to 0.0691 divided by 2 divided by 2 times alpha 1.37 multiplied by 10 to the minus 7 multiplied by t, and from that you can solve t as 161507 seconds, which is 44.86 hours. Okay, so why do we get this ridiculous answer? The reason for that is that with this approach, okay, we are looking at a body which is infinite in that direction. Okay. And in this case, if we want to solve the temperature at the center, okay, if that is now the body, okay, and it should be infinite in that direction and infinite in that direction, we want to solve the temperature here, which is now changing. So our body temperature is changing. So this derivation has been derived for a body where the body temperature remains constant. However, the changes are close to the wall. So this system, or this approach, could have been used if we wanted to know very closely to the wall of the wine bottle how the temperature changes as a function of time. But in principle, cannot use it. It is not an appropriate body. Okay? Do you all agree with that? Okay. Now, the last question, question 5, is to say, well, let's consider the body as a short cylinder. Okay, short cylinder. And this short cylinder now will have a diameter of 69.1 and a length of 200 millimeters. Okay. And now we want to solve the temperature at that point there. Okay. Right, now for a short cylinder, there's the short cylinder. For a short cylinder, the solution for a short cylinder is the solution of a cylinder multiplied by a wall. Okay. So the non-dimensionalized temperature for XRT would be equal to the solution for a cylinder, it's a function of RT, multiplied by the solution for a plane wall as a function of XT. And now, we would like to know the temperature at x0, okay? At r0, we would like to know it as a function of time. It's equal to the non-dimensionalized solution for a cylinder. R should be 0, multiplied for a plane wall, and x should also be 0. So that is the solution that we need to get. So let's firstly look at the solution for a cylinder. I see I'm running out of time, so I'm going to go a little bit faster now. So for a cylinder, it would be equal to A1e to the minus lambda square multiplied by tau. Again, these terms disappear because it is r equal to 0, and we make the assumption that tau is larger than 0.2. Okay. Calculate the Biot number. The Biot number is equal to h r0 divided by k. Again, it would be 30.14. So the solutions in terms of A1 is the same as previously, 1.597, and lambda 1 is equal to 2.326. Okay. And tau, the non-dimensionalized time, would be equal to alpha t divided by r0 squared. And we can write it as 1.37 multiplied by 10 to the minus 7 multiplied by t divided by the diameter 0.0691 divided by 2 squared. And then we can write down the equation for the cylinder as 1.597 multiplied by e to the minus 2.326 square multiplied by 1.37 multiplied by 10 to the minus 7 multiplied by t divided by 0.0691 divided by 2 squared. So something like that. Okay, now for the plane wall. Okay, for the plane wall, again, we can say the non-dimensionalized temperature is equal to A1 e to the minus lambda square multiplied by tau. Again, we assume or hope that tau is going to be larger than 0.2. Okay. Calculate the Biot number, which in this case is equal to HL divided by K. Okay. What is L in this case? L is that distance there for the plane wall, so it is 100 millimeters. So L is 100 millimeters, so it's 500 multiplied by 0.1 divided by K, which is equal to 0.5732, and that would give us a Biot number of 87.23. And again, we can, from the tables, go and get the values for A and lambda. Okay. I'm just calling them A2 and lambda 2, so that they are not the same as that 2 there. And the non-dimensionalized time, in this case, would be equal to alpha t divided by L squared. Okay? So it is different than that one there. L is now 0.1, okay? And you can calculate tau 2, and again we can then write the equation for the plane wall is equal to 1.273 e to the minus 1.553 squared multiplied by 1.370 multiplied by 10 to the minus 7 multiplied by t divided by 0.1 squared, something like that. And the solution would be the multiplication of the two. So the solution would be, at the center, would be equal to the solution for the plane wall and the solution for the cylinder. That one we can calculate, the non-dimensionalized temperature. Everything is known, and from that we can calculate the temperature as 4,198 seconds, which would be about 70 minutes. Okay, now very importantly is this approach valid? What is the approach valid? Surely it is, of the three methods or the four methods, the best one, but there is a caution. And that is that now that we have the time, we can actually go and calculate tau 1. And tau 1 is 0.48, but tau 2 is equal to 0.057. Okay. So actually that one is not valid, which means we have to take into consideration more terms. When we calculate that, that is the only negative thing that we can say about this approach, but in general it should give us good answers. And you can also see the answer is very close, of 70 minutes is very close to that of the previous approach, which is about 67 minutes. Right, ladies and gentlemen, any questions on the fundamentals, the approach? Nothing? Thank you very much.